What I'd like to introduce is our last presenter for today, which is Dr. Olga Barron. Her presentation is Opportunities for Desalination in Australian Agriculture, and the two organisations are CSIRO and Valoriza Agua. I'd just like to introduce Olga for those of you who have not met her before. Dr. Olga Barron joined the CSIRO as a hydrogeologist in 2003. She's the Principal Research Scientist with the Water Research Group within the CSIRO Land and Water Division, and leads the water-sensitive urban design environmental projects for the CSIRO's Water for a Healthy Country flagship. Olga was awarded a doctorate in Engineering and Geology and Environmental Geology from Moscow State University in 1986, and a doctorate in Chemical and Environmental Science from the University of Limerick in Ireland in 2000. She previously worked as a senior scientific researcher for the Research Institute of Survey for Construction in Moscow and as a senior research fellow at the University of Limerick in Ireland. Thank you very much.
Thank you. Now you know everything about me, or nearly everything. How are you going? It's last presentation for today, so I hope I have control, and hopefully it will be a little bit of change of pace. It's not as technical presentation as other was, and it's more about application of desalination technologies to one of the most important industry in Australia, which is agriculture. So I'm going to talk about just a little bit about introduction and the concept and what make or break desalination opportunities in agriculture. Spend a little bit of time on our project development, national and regional assessments, and case studies, which hopefully will yield some trials. So as you already know, the project is collaboration between the center, CSIRO, and Land and Water, two divisions involved in that, and the Valoriza Agua. We started last year, and this is up-to-date results what I'm going to present. So the main objective of our analysis is to provide national assessment of feasibility if desalination could be useful in agriculture, which could potentially address the issue of water security or variability, and kind of provide more secure water supply for agriculture. A little bit about desalination worldwide. Currently, we as citizens of the world produce 300,000 gigaliters of water a year, which compose only 1% of total water use in the world. Agricultural sector, on the other hand, uses about 60% of total water in the planet, and desalination contributing very small proportion of its capacity to desalination to agriculture in this stage, which on these global numbers compose 0.05% of contribution to water use in agriculture. However, this is world, it's like average temperature per hospital, but there are places where the desalination used much more efficiently and successfully. Spain is one of those places. About 22% of the desalinated water used in agriculture. In some places like Tenerife or Canary Island in general, the production of desalinated water actually make economy going with water supply to tourism and to water production for tourism. So really it is a success story, though I have to mention that agriculture in Europe heavily subsidized. So this might make a difference. In Qatar, for instance, another country which they use about 13% of desalinated water for agriculture. Saudi Arabia produce 1/3 of desalinated water in the world. Well, you can calculate what does it mean 0.5% go to agriculture in Saudi Arabia. So maybe it's much more than in Spain when you looking through the gigaliters. So the general concept which we try to investigate and prove is that when you consider desalination used in agriculture, it's not one or another. It has to be considered as integrated food, water and food production. There is specifics in water supply need in agriculture, and therefore there are also opportunities for desalination to support those. So first of all, it's still considered to be a very cost intensive water supply option, desalination. Therefore, worldwide, it's mainly brackish water used for agricultural purposes, as it's cheaper. Brine disposal, therefore, big issue because inland water desalination, groundwater desalination, or surface water, to that matter, is challenged by the cost and need to deal with salt, brine, and salt. We also need to be very mindful of the users, so it's really relatively small plants and has to be reasonably simplified because of the use in rural, more often circumstances, and by people who potentially not particularly what I say, what should I use without offending anyone? So we also need to make sure that there is feed water resources available, meaning that we have to have some way brackish groundwater or surface brackish groundwater. In Australia, it's actually more groundwater because surface water doesn't flow often when you need water, so it's not particularly viable resource. And also the proximity to demand, because the distribution of water become very expensive. So this component potentially need to be very carefully considered to reduce potential costs. And when we consider agriculture, we don't need drinking water standards. Reverse osmosis water pyramid is really too much. 750 milligram per liter, this is considered just the water quality which plants tolerate. It was also demonstrated that use of desalination for agriculture allow to increase productivity. In Spain, the data suggests up to 50% of increase of productivity per hectare. And also water use efficiency. Worldwide, about 1/3 of water used for irrigation is lost to evaporation or runoff or deep drainage. So therefore, you can say the cost of water which is really used is 1/3 of what, 3 times of what is otherwise would be, or just whatever people pay for water which they lose. It's also most often desalination used for high-value crops, which can handle a little bit increase in the water price. But also there are other benefits. There is opportunity for recovering, for instance, of saline soil, which also improve productivity and quality of produce. But when we talk about Australia, there are a few points which I need to mention as quite differentiation from other world. We have labor market and labor market is small, labor cost is high, and the labor market is really concentrated a lot in few areas. We have particularly high infrastructure costs, particularly when we're talking about remote areas, which is also add quite a bit of cost to any new development, but also limited support from government in terms of subsidies to agriculture. So a little bit about Australia. I think you all know that, but red center, this is common use of colors, but also very much in line with what Australia is, red middle, desert and arid climates, this red and brown colors. So majority of agriculture and settlement along the coast. Australia agriculture use in line with the world, about 65% of total water use in Australia, and 90% of it used for irrigation. Quite substantial gross value in agricultural product, nearly $42 billion a year. And 30% of it is from irrigated land. So it's really a large contribution to Australian industry economy. However, about 80% of water food production is exported. So therefore, here we have quite a bit of difficulties related to our high Australian dollar value at the moment. So it's make this export quite difficult, and therefore, whatever in any way increase the cost of production is not particularly welcome. So this is density of population in Australia, so a little bit around the ages. 100 people or more per square kilometer, so it's really, if you look at Europe, it's an order of magnitude greater. And this is where most of agricultural activity happening as well, a little bit on the north. When you talk about gross value, it mainly comes from cereal for grain and seeds, and also from meat, cattle meat, so beef. But when we talk about agriculture, the highest value is coming from fruits, vegetables, and dairy products, and this is where potentially desalination could be most effective in terms of this water supply. This is illustrating the support from government in the different places in the world. New Zealand is the only one who has lower than Australia, and I don't have Spain per se here, but European Union about 23%, though some of European countries much higher. So it's hard to compete, high dollar, low contribution, so it's very difficult competition. When we talk about water resources, how they use in agriculture, nearly 70% of irrigators using surface water irrigation. This is how it looks like. So it's really unlikely that desalination can support this type of water kind of irrigation practice. There is much smaller amount of the other more efficient way of irrigation, but it's quite substantial savings. When you look at the grapes, for instance, irrigation, minimum, mean, and the maximum from number of observations as water use per hectare for irrigation when you use flood irrigation. And on your right-hand side, it's data regarding drip irrigation. Again, minimum, mean, and maximum. So you can see that in some circumstances the efficiency could be 9 times better. So therefore the cost per water is proportionally. It's obviously much more savings you can do with it. And when I talk about salinity, also the question of soil salinity, which is also related to water salinity, there is obvious opportunity to increase productivity. So you can see a number of crops stated on the left-hand side. The straight lines, solid lines, indicate where the productivity is between 75–100%, and then when you come to more silane system, the productivity drops up to 50% of maximum. So therefore, moving from this end to this with providing better water quality actually can increase quite substantially productivity of agriculture. So this is where opportunity lays in our view. We're just bringing two of these industries together in a way considering the needs and opportunities which bring from both directions. So since we was targeted with national assessment, some of analysis were, or most of analysis during this project is desktop study, but we look at the few aspects of it. So the first, in terms of national and regional assessment, we look at the where current irrigation practice occur and how where geographically potentially we can deal with desalination, which can be in proximity to irrigated area. We also look at the groundwater sources as water resources for irrigation, for desalination. As I said, surface water has intermediate nature mainly, and as a result wasn't considered. Wastewater, which is one of the important and probably quite already used water, it actually was under investigation of other projects, so we didn't include it in ours. And wastewater from mining operation, for instance, like coal seam gas, also is under investigation of other projects. So we only consider natural water resources as such. And then, since it's groundwater, we needed to look at the implication of disposal need in terms of cost on total kind of water production cost. We look at the water delivery cost and a little bit about groundwater abstraction cost. So when you look at where currently irrigation happening and where it's potentially desalination could be utilized, so this is typical factors analysis type of approach. When I look at the distance from irrigated areas with you can see the ranges we took and distance from towns. Distance from towns was one of the important parameters. First of all, you talk there is infrastructure most likely around these places and labor, but also opportunity for use desalinated water for something else. If we know that irrigation probably doesn't require 365 days a year of water supply. So with some factoring analysis, this is our area which we're suggesting that there is potential for this way we can look at opportunity for desalination to be used in agriculture. And then we excluded number of parameters, environmental protection zone, topography. We found that there is no much of agricultural irrigation activity in the area with surface elevation more than 600 meters above the sea level. We also look at the groundwater resources and excluded those which are of low productivity or low and medium. Some of this also could be excluded because they are not particularly productive. So if you exclude one or another, this is our final destination where potentially we can try to investigate if there is any options for desalination. There is another need to consider if it's come to the point that seawater desalination is important to be considered, and seawater disposal, particularly for brine from brackish water desalination. The recently implemented marine reserves has to be taken in consideration. Environmental implication and law in Australia are very strong, so this is potential of some limiting opportunities, great barrier reference. So when you look at the groundwater resources, these are sustainable yields. It's how much without you can abstract groundwater in those areas without much of the impact on groundwater dependencies otherwise. And it's if you look at the need for this irrigation, when we talk about 1 to 5 megaliters a hectare, majority of yield allowed is much lower. So it's potentially could be a question if groundwater could be used everywhere. The thing is that this data is mainly related to surface, to fresh water. Nobody really did much research on brackish water in Australia in terms of defining their resources, but it probably reflects the property of aquifers as such, and therefore could be inferred to brackish water as well. And then another component of groundwater, it's not infinitive resource. You have to consider renewable part of it. And therefore groundwater recharge is one of the aspects which also need to be considered. So when we talk about 1 megaliter per hectare, which is quite low use in agriculture, it's really some outer side of this area which could be receiving enough recharge to keep it going. Well, not only yields, but groundwater salinity and water quality not particularly well studied through the country. So this was a lot of time we spent trying to find information about that. This is Western Australian data, and you can see there is quite a bit of saline and brackish groundwater resources in the state. Considering that this is Perth Basin and Canning Basin somewhere here, this one, there are quite a few areas when groundwater is just marginally brackish. Okay, so talking about disposal and the other component of specific component of cost in relation to groundwater, we try to look at the kind of holistically into this issue. So when we need to abstract groundwater and reticulate to the plant, so this cost is one of the items. When we talk about desalination, there is obviously a number of issues here. Reticulation to disposal basin, and there are a number of options for disposal facilities. And talking about agriculture, it's potentially the need to have some water storage, for instance. But also there is additional costs related to establishment of this enterprise, and you people who work in industry knows how much more expensive to build something in Karratha than in Perth. So you probably multiply by 2 all costs which you acquire here in Perth. And therefore, the distance, this would also affect quite a bit of this assessment, could affect. But based on our analysis of water prices for agriculture, it's really probably, well, based on our analysis, we're suggesting that under no very unlikely that any enterprise will buy water for more than $1.2 per kiloliter in agriculture. This based mainly on Murray Darling work. So in Western Australia, farmers could pay 18 cents per kiloliter. 50 cents considered to be very expensive. So therefore, this analysis needs to be taken with kind of absolute maximum margin as such. So when we look in groundwater abstraction, I don't have illustrations for these points, but I just need to mention that the thicker is aquifer and more productive aquifer is, the least cost is required to abstract it. So instead of, it's actually question of installation of bore, but also reticulation. So the one deep bore produce much more water with less reticulation requirements. So we're really looking, if we want to reduce cost, we're really looking for high productive thick aquifers with brackish water. And then what we looked mostly in our analysis was disposal. And in this disposal, it's evaporation ponds. Evaporation ponds are obviously more effective in the area where there is high evaporation potential. And also it's depend on how much water we produce and how much reject water we produce. The cost could vary. So in what follows, I just will be considering the cost for desalination and evaporation disposal as add-on to desalination plant. So we used, since varieties of circumstances in those areas which we identify as very difficult to pinpoint, from yields, concentration, energy infrastructure, and so on, we decided to look at the kind of the ranges of possibilities. So from some analysis which we undertook, the plant cost, capital cost for plant, the ranges was considered to be from 600 to 1,200,000 megaliters a year, as capacity as megaliter a year. Proportion of this cost in total water production is between 0.3 0.5. Total cost of water production, this is per minute produced, is as much. And the recovery rate, these ranges, as well as ranges of potential cost for installation of brine evaporation pond. So we had series of kind of randomly selected numbers in this interval, and we ran Monte Carlo simulation trying to understand how many of these combinations can produce water of price less than $1, 90 cents, 80 cents, 50 cents. So really the result of this analysis could be illustrated by this distribution curve. What it shows is how many out of total of in excess of 8,000 combination which we produce, how many of this combination can be below $1, 50 cents under different evaporation capacity in the country. So what it's suggesting that if you have 1,000 millimeters a year of evaporation, roughly Perth condition, we have only about 13% of probability that the cost will be less than $1 in somewhere in Perth. And if we have 3,000 millimeters a year evaporation capacity, this probability jumps above 60%. So if you look at this transact, so we're really looking in circumstances where we are in this area. So if you look at the transact along some of these costs, so transforming this figure a little bit different way. So we have evaporation potential on the X and probability of the Y, and each line corresponds to maximum cost we want to achieve. We see that really, if you're talking about this area where the most of our zones which we identify exist, we're really struggling to get any of combination above certain dollars. So if you want something which is less than 60 cents, there is practically no chance to get it if we need to dispose this brine in inland facilities. If this presentation or analysis is very useful to translate this data on in spatial terms, so we know where evaporation potential, how different, how it's changed across the country. So what this figure suggests that in order to get less than $1 in identified areas, we really have only about less than 40% chance to get that. But if we need to get to 80 cents per kiloliter, it's only 5–10% that we can find combination of those parameters which can meet that. When we look at the distribution curve, absolutely maximum cost which come under all of this analysis is between nearly $3.50 to $2+ in the area of where our potential desalination could take place. So this is where what sort of values we're talking about if you don't get into any specific analysis in terms of, well, within our constraints, this is what most likely we are going to have there. When we look at the sensitivity of this probability to different component of our estimations, what comes to as a result of this analysis, the most sensitive in probability of desalination to be applied is recovery rate. So the higher recovery rate, there is much greater chance to get desalination going. The next important one is disposal basin, and then proportion of cost, total cost and water price. And apparently the least importance actually is water price itself. Also what is interesting is that there is reduction in this sensitivity when you go from lower evaporation to high evaporation districts. So if you look only on 90% of recovery in desalination, the picture becomes much more promising. So really we're talking about higher percentage of high probabilities of desalination to be adopted. Can we do 90%? I guess it's a question for you guys. But if you go to lower, even only to 80%, we again in square one, so it's become quite difficult to get a combination of parameters to work for us. Well, when we look at the one of those plots which we saw before with probability equal to $1 per kiloliter, question of distance from this plant become very crucial. So in order to have our irrigation districts, for instance, within 10 kilometers, the probability of reaching $1 fall from above 70 to 40%. If we are within area of, so this is Perth actually, so within few kilometers from desalination plant, it's really become more expensive to transfer this water. So distance from the plant become quite important parameter. Well, as I said, desalination, seawater desalination is not commonly used in agriculture, and though I'm not going to talk about much about it, I just wanted to show you that desalination in seawater desalination in Australia is actually even much more expensive than in other places, so it's probably very unlikely to be used for irrigation using just common approach. So this is how much plants in Australia produce water a year, and this is how much it costs. For Perth, nearly $1, Sydney, Perth, Adelaide, Melbourne. So it's really Melbourne produce water similar to some other countries which produce 100 times less water. So economy of scale in Australia work a little bit different other direction. Okay, so this was about desalination. One thing I need to mention, that desalination related to pyramids. So if we can increase water production by blending, bringing water quality to the water quality required for irrigation, those numbers become much more promising. When we talk about case studies, we were trying to be more specific to locations where we have some information on what's happening. And these case studies include also assessment of agricultural activity. So really when you look at the framework of analysis of economics for any farm production, water is one of these components. So we can use some of this in our analysis. So what this framework use: yield of produce per hectare, unit price, irrigation system cost, capital cost, and variable cost, and here where the water is. So you can see that yields could be quite different for different production unit cost, capital cost of investment, and so on. So bringing it all together along with desalination can assist us in analysis of economics of these systems. So one of the case studies, we have few of them. I'll go through some level of detail with one and just mention others. Dalby, there is only few brackish plants in Australia in terms of water supply in agricultural regions. They're all for drinking water supply, and Dalby has one of them. It's brackish reverse osmosis plant, and we try to see what sort of agricultural produce can be you can use this water, and if there is any way to have profit out of it. So when we use the water directly from the plant without blending or anything, which is probably even dangerous in this circumstance, but it's mathematics, we can do whatever we want. In a way, we come up with only few produce which can still be profitable. Cherries, strawberry, turf. Not probably something which feed the world from hunger, but this large return from investment is what drives this one. And then we try to investigate what sort of opportunities lies in changing some of these parameters. For instance, we reducing water use from 100% to 70%. And you can see there is some increase in profitability if you use less water. And some of the, under some circumstances, some of this system become a little bit on positive in terms of profit. When we consider changes in productivity, actually quite few of them comes to positive territories now, saying that increasing in productivity and reduction in water use, when we consider them together, for instance, plus a little bit of blending of water with other waters, it's actually quite a few of them become much more profitable. So this is the way to meet one in the middle, desalination versus agriculture. And when you look at the sensitivity of profit to changes in some of this practice, you can see that the highest sensitivity is productivity or price, because it's one or another. We didn't do it combined, but it's just one or another. So productivity is the key, and actually the water use and blending is much lower impact. So this is logarithmic scale, so it's 1 against 40. So really focusing of how we can improve productivity in agriculture using desalination technology is the key. And as a result, what comes to mind immediately: effective water use, productivity, control condition, greenhouses. And one of these operations currently are actually very successful in South Australia, called Sundrop. They're using seawater, which is against the rule, which I already mentioned. They use distillation, which is much more expensive. The water price is between $2 and $3 per kiloliter, which is above our values, and they're still profitable. So this generic assessment has to be analyzed for individual cases, and this is why we think the value of this project become much higher if you do that. So this is Sundrop, what I mentioned to you. Solar panels heating the oil which comes to 160 degrees, and this water is this heat used for condensation, demineralization of water. They reuse about 60% of water which comes through the system. They're cooling these plants. They sell tomatoes and they sell cucumbers and capsicums, and they're extending now to another enterprise from few hectares to 20 hectares, I think, and it's about $30 million enterprise now. The other area of our interest, when we look at the Mylap Horticultural Center, this is where it is. This is Binyapa's desalination plant. It's Western Australia, as you realize. Groundwater become more and more brackish in this area because it's recycling. They use this water and apply it again. So groundwater become brackish, though it's also coastal aquifer, very substantial groundwater resources, but brackish. There is opportunity to dispose this water to the ocean with cost cutting, hopefully that we can use some analysis done for Binyap if we need to do that. And also opportunity to advance productivity if we use more the better water quality. We hope that this will become our trial, and we're trying to define how we can do it here. Then there is vineyards in South Australia which has brackish water. They have also wastewater, quite substantial amount, with higher salinity than they would like to when they use it for vineyards. And therefore what we're trying to investigate, can we use groundwater desalination to blend it with wastewater which they already have, because it's obviously have nutrients and other parameters and other components, so that that part of the water become more usable. And also it's mean that we don't need a large amount of groundwater resources treatment and disposal. So this is one of our case studies. Then there is one again in Dalby. It's for for feedlots, which is quite promising because water in feedlots required practically all year round. This is different technologies. It's they use ion exchange and also trying to bring some mineral recoveries for irrigation, for soil conditioning. They use, actually I said that we are not involved, but they use actually coal seam gas water for this water supply. Spain, we're trying to see if we take all component of system which they use in Spain and try to translate it to Australian condition and Australian cost, Australian labor, Australian market, and see how it's stack up, because they, as I said, they really have very good long-term experience. 40 years they use desalinated water for agriculture. The other aspect we try to look at is new establishment. You know, there is a lot of discussion about development of agriculture in the north, and the question of if in any circumstance we can help for this with production of desalinated water. We use OR2 data, keeping in mind that we don't need extra water for OR2. They have enough water in their water supply from stage 1. But what we used was for analysis of how much it costs to establish new regional development, how much water you need to bring there to make it viable. There are many other issues with that. Water is probably the smallest one as such, labor, diseases, and other things. But a lot of environmental and Aboriginal right discussions. So they spend about half $500 million for establishment or two, and this is only during last few years. So it's very expensive. But when you consider how much water they need for proposed sugarcane use, it's greater than second desalination plant in Perth. It's more than 160 gigaliters a year. So it's probably still more expensive than the amount of money they spend to establish this. So it's probably not particularly possible. So, and here's the results. So we would really like to reinforce this concept of integrated water and food production, because combination of both can be the way forward to make it more possible in use of desalinated water in agriculture. as I hope I convinced you that the reduction in water use and increasing productivity actually can offset the relatively high cost of desalination. However, if you use flood irrigation, it comes at cost to replace it with sprinklers or anything else, so nothing comes free apart from rain when it comes. And therefore, the most likely application for new developments is greenhouses. Talking to the Department of Agriculture, they are saying there is a lot of interest in developing agricultural areas north from Perth, but there is only brackish water there, so there might be opportunity to build on this analysis there as well. However, we know that everything, just population growth, food security, climate change, fresh resources overuse, land degradation, may in future, and probably even near future, make desalination more effective for agriculture, particularly if we can make all these plants easier and cheaper, easier to use and cheaper to produce, something like the presentation this morning, reuse of membrane. Probably for agriculture it's one of the best way to try how to adapt that wider. So the probability of establishment of this combination is likely when you have when we're dealing with groundwater, with brackish groundwater, with highly productive groundwater resources, lower salinity because we can do more with this water, less high recovery rate, less disposal, more chances for blending, and proximity to irrigation area. This is why we're kind of trying to see if MyLab could be, meet all of this. And we need to consider also that it's probably more likely to be for high-value agriculture. However, we talk about wheat, which is one of the highest export product anywhere. You talk about 2 tons per hectare production. Western Australia's dryland agriculture, but 9-10 under irrigated practice in the east. And quality of the grains is much better, so therefore price could be much greater. Even this highly used worldwide produce might benefit, and again it's economics assessment and also opportunity to bring more tuned desalination technologies for irrigators. And I would like to finish with acknowledgement to the center team which work on the project and CSIRO flagship water for healthy country. Thank you.
Thank you very much, Olga.
Yeah.
Questions, please. I'll just lead off with one, if that's okay. I would think that one of the critical factors, certainly in large volume usage in agriculture, will be the blending ratio. And obviously, it depends on the TDS of the source water. Do you think that blending efficiency and ratios would have a big impact on some of the applications? I know you had one sensitivity there, talked about a 20% blend, but do you think blends of up to 50% of brackish water are more likely, or is that something that's...
Well, it depends on the source of water. If it's about 2 grams per liter, you can go up to nearly half of increase of the cost, double the production. If it's come to 5 grams per liter of brackish water, then it's only 10% increase in water flows, increase in water production, which could be useful. Therefore, it's question also, we would like to work with less soil and groundwater resources where you can produce much more water.
So the TDS was about 750 or?
750 milligram per liter, yeah.
Okay. So brackish water is maybe between up to 2,000 TDS.
Well, when it comes to 2,000, it's become very little you can add to. But also why blending is useful, because obviously you all need, better than I do, that there is a need to fix the ion balance in the water. It's too corrosive. So any post-treatment may be also offset by blending. So therefore it might be less cost related to post-treatment. But also opportunity to add fertilizers, for instance, and some nutrients in water supply, which reduce cost of distribution of nutrients in addition to distribution of water. So there is obviously opportunity to look at the just blending. Talking about MyLab, for instance, the deep aquifer there is quite clean in terms of nutrients. Upper aquifer, which used for irrigation, has nutrients, organic matter, and so on. So desalination of the aquifer, of groundwater from deep aquifer mixing with shallow aquifer actually increase the productivity, but also allowed to add some nutrients which are already in the water. So it's art.
Good. Thank you. Any other questions, please?
I think everyone's so tired. I just like to hear. Can I ask questions?
Sure.
But nobody asked me. William, maybe you can comment on opportunity for reuse of membranes in terms of agriculture, like gravity-driven treatment and so on. Is it something which you can see possible?
Well, obviously you can't do gravity-driven desalination. Wouldn't that be the dream? But of course, if there's a need for RO desalination in agriculture, especially with your low water quality requirements, it's exactly the application that we're looking for direct reuse. I mean, you get a slightly lower salt rejection in the membranes, hopefully significant savings in the capital costs, and it's a perfect application for it. Exactly. Yeah.
Would be useful to do some calculation, maybe, if you have something to assist us with, because as I said, that cheaper, lower cost in desalination technologies for agriculture is a key.
Well, yeah. The numbers that are thrown around for membrane costs for desalination plants is obviously low. We're talking less than 5% of membrane costs in the overall capital cost of setting up the plant. But you know, every bit counts, I guess. Yeah.
Okay. Thank you.
Good. Any other searching questions?
Nobody's searching soil in agriculture.
You've done an excellent job of summing up. It's certainly an interesting proposition. Very interesting. I'm sure you've looked at Israel as well, what they're doing over there, using a lot of sewage effluent as well, obviously.
Well, as I said, we are not really, we excluded this from scope of work because one of the projects funded by Center for Excellence in Recycling, they fund one of the projects of desalination in wastewater reuse.
Okay. Well, I'd just like to thank all of our presenters that have been here today, and very much appreciate it. At the moment, I'd just like to thank Olga once again and thank you for your presentation.